Welcome to this session tutorial 3. So, here I will explain one simulation. After I explain, then that those files will be shared in MS Team as well as in WhatsApp group. Okay, this I already explained in first class. Okay, so now today we will talk about this converter, power converter, and a part of this power converter, because when we are going to extract power from the renewables. So, as I explained for hydropower plant, we need AC to AC converter when it is connected to the grid. Here we try to configure it for AC to DC microgrid. Okay. So, here this could be the configuration. These two configurations need explanation. So, first is for solar PV, another one is for mini hydro power plant. Now, what you have here is, so in this figure what you have a DC microgrid for both the cases, then you have solar PV or you can have mini hydro power plant. Now, here sits the DAB converter, okay, dual electric bridge converter. So, before that let me explain you components one by one. Okay. So, here you see, when you have microgrid or any grid, that means what? This DC bus DC bus that we have here, this voltage is fixed or regulated to a certain voltage, okay, for both the cases. Now, this part is on the grid side or load side. Now, this side is the source side. So, whether it is solar PV, whether it is hydro power plant, as I explained in the very first day, that you have to extract power at MPP. So, since solar output is DC, so we are using a DC converter. When there is a mini hydro power plant, so you have AC here, then AC, and then here you have DC. So, there is a AC to DC conversion. So, here also it is DC to DC conversion. Now, for power to be extracted at MPP, the criteria is this DC link voltage must be regulated. When this mini hydro power plant I explained connected to AC grid. So, we had configuration, if you do not remember, let me draw it once again. So, what we have is, we have the machine, then we have back to back converters, and then you connect it to the grid. So, this is AC to DC, this is DC to AC. So, this is grid and this is the machine, induction generator, or sorry, this converter fed synchronous machine. Now, here I told you that this converter will be doing MPPT and this converter will do DC link voltage control. Okay. MPPT and DC link voltage control. Now, here instead of grid, what we have is microgrid, where the voltage is DC voltage, and also this voltage is substantially low compared to the voltage for mini hydro power plant, or this is not same as this voltage. These two voltages are not same, and this voltage I told you that this voltage could be higher voltage and DC microgrid voltage will be comparatively much lower. So, there is a voltage mismatch between these two ends. So, if you remember, for back to back converter connected to the grid, we had transformer to match the voltage. Okay, we had transformer. Here we do not have any transformer. How to do that? Okay. So, configuration that we try to achieve here is, let us say if it is a mini hydro power plant, then this is the source, then we have AC to DC converter, the DC link voltage is generated, then there is a DC converter and then it is connected to the DC microgrid. Now, what could be the problem here? If you use a DAB, what or in this configuration, what is the challenge? What is the challenge that we have? Anybody can tell from offline online participants? What could be the challenge? You just see this image, see this configuration and you tell me, you just try to figure out what could be the issue. If we use so instead of back to back converter connected to the grid, instead of this, so here this DC link voltage was fixed or regulated through this converter, and this was MPPT was done by this, and this is only achievable when this DC link voltage is regulated. So, we need to regulate this DC link voltage, and this is already regulated as it is a DC bus voltage, DC bus of a microgrid. So, this voltage is to be regulated. Previously, it was a back to back converter from the grid, we can able to regulate it. Now, we have a DAB DC converter. Now, DAV converter cannot regulate DC voltage, this output DC voltage, if it is SPS. Okay, that I will come to, I will come to that. Okay. Now, so that means in this configuration, this will do MPPT. So, this is this one, this converter is this one, MPPT. Then you have a DC converter which will control the power flow, which will allow the power, the maximum power to flow and to the DC microgrid. Now, the two things that you need to think of is how to regulate this DC voltage. This DC voltage is already regulated, and there is a power flow which will depend on phase shift angle, external phase shift angle, power flow, external phase shift angle. So, it depends on external phase shift angle. So, MPPT power is generated, that is that control that I explained in first lecture, that that rotor speed control will be done, and the DC link voltage has to be fixed. This DC link voltage in this configuration has to be maintained using this DC converter. How that you think, how it can be achieved, that the DC link voltage you want to maintain this, so voltage control. So, you must to have a voltage control, the control, it has to be, the DAB has to be in voltage control mode, so that this DC link voltage can be maintained at a fixed voltage, and at the same time you do this firing angle, external phase shift angle control, so that power can be delivered to the DC grid. Now, the question is here, since it is mini hydro or solar PV, whatever it is unidirectional in nature. So, power only flow from source to the load. Here also power flows from source to the load. So, you might not need two active bridges, active bridge here, active bridge here. But the question is, when you are going to regulate this DC voltage, when you need to regulate this DC voltage, you will see you need to have a bidirectional power flow. As I already explained yesterday, when it is a DC converter and it is going to maintain the any DC bus voltage, it has to be bidirectional in nature, otherwise that cannot be achieved. Okay, is that clear? So, now with that, if it is so, in addition to this, just let me explain you another converter where you have similar kind of DAB converter kind, but it is not dual active bridge, it is single active bridge. So, what you have here is so, this is an active bridge. but this is a diode bridge. So, as I told you, when it is diode, it is always power flow in one direction, it is in from this side to this side. This can also be used, but since you are trying to maintain DC voltage using this converter, it is using this diode bridge rectifier will not do. So, what you have to do is you have to use a dual active bridge converter, and you have to see, you can think on it how this DC link voltage can be controlled, so that MPPT can be achieved and that MPPT power can be delivered to this DC microgrid. Any query from anyone online and offline, I will address it, because understanding this configuration is necessary. So, today in simulation what we have this DAB DC-DC converter, which you can run using any of the modulation techniques that I explained yesterday, SPS, DPS and TPS. Okay. So, this is this configuration I have in my simulation. So, here you have DC voltage input, DC voltage output, battery is the output connected at the output. There is a high frequency transformer link, there is an active bridge here, active bridge here. Okay. So, using this modulation scheme, you can run the DAB converter, and then you can see in which modulation scheme you can able to control or maintain the output voltage here. So, here if you see here what we have, this is a battery. So, battery charging can be done using two methods, CC and CV, constant current charging, constant voltage charging. So, constant current charging is like irrespective of battery voltage, you are pushing a constant rate current to the battery. It could be, so if it is a DC fast charging, it is almost like 1.2 C or 1 C, something like that. The rate is like that. So, you charge at constant current up to 80% of SOC, and then you move to, otherwise if you continue it, then the battery could be overcharged. Okay. So, 80% of SOC, and then you move to constant voltage charging. So, how you can achieve this constant voltage, that you need to see whether it is achievable using SPS, EPS or DPS, that can be done or not, that you can see. Okay. So, this thing I already explained, SPS, EPS and DPS. So, in SPS the internal angles, so these are the internal angles, internal phase shift angles which are 0 for SPS. So, in the simulation model that we are going to share, there this you can adjust both alpha 1, alpha 2 and alpha 3, all these angles you can adjust, and you can accordingly you can get the results. So, alpha 1, alpha 3 will be 0 for SPS, and you play with alpha 2 and see the power flow whether it can be achieved or not, and also you can see whether there is negative, that I talked about back power flow. I talked about, you can see whether the back power flow is there or not in SPS, and also how this back power flow can be minimized in EPS. In DPS you can see whether this constant voltage charging whether we can achieve or not, and then TPS where we have both internal phase angles are not, internal delay angles are not same, and there is an external phase angle as well. Okay. Now, these are the simulation parameters. These simulation parameters are mentioned in this simulation parameter file that will be shared with you, and this is the DAB converter simulation file. There you have the DAB converter where you can control the phase shifts. This phase shifts, variable time on transport delay block is there. These blocks are there. By adjusting the angles here, time delays here, you can adjust both alpha 1, alpha 2 and alpha 3, and accordingly you can achieve SPS, EPS, DPS and TPS. So, simulation parameters are here also, it is given the same simulation parameters, and then this file will be shared. So, what you have to do is you run the, so all of you, we assume that all of you have MATLAB. I have saved this MATLAB file in a lower version of MATLAB, so that irrespective of if it is typically some recent MATLAB version that you have, then also you can run it in online also. I do not know whether this time step will be, you have to keep time step 10 to the power minus 6 or so. Okay, acha. One thing I supposed to tell you that I personally prefer you always run MATLAB in fixed time step, not variable time step, and the time step Ts generally I prefer e to the power minus 6. For DAB we are running at 1 e to the power minus 7, though it is taking huge time. Okay, this you can try 10 to the power minus 6, you can try time step fixed time, but you run it at fixed time step, this I prefer always. Okay. Now, for your reference what we did is we have kept the waveforms. So, how the SPS waveform will look like, how EPS waveform will look like. Okay. So, here you see in SPS waveform both are square wave. So, since both are square wave, that means here that delay alpha 1 comma alpha 3, this you make 0 and then you run it and then you will get the result. You run it for different value of alpha 2 external phase shift angle. External phase shift angle. You run it for different values alpha 2 and see how much is the power flow, and this is the power flow waveform that you will get in SPS with some negative. So, these things you have to observe. Then in EPS, if you run in EPS with alpha 1 not equals to 0, alpha 3 equals to 0. So, that is why the secondary voltage is a square wave, primary voltage is a quasi square wave, and then you alpha 2, then you play with this and you get the result of output power. In DPS what you do is, in this is EPS, another waveform EPS, then in DPS, so alpha 1 equals to alpha 3 not equals to 0. So, this internal phase shifts are there for both the phasors. So, you can see here when you are doing, so this is when alpha 1 equals to alpha 3 equals to 0 for SPS. In DPS what we do is we introduce some delay. So, if you introduce some delay, then it will be a quasi square wave. So, the waveform will be shorter, but this will be same for both of them. So, these phasors are going to be shorter for both of them. So, this angle is alpha 2. Okay. So, this is SPS and this is DPS. Okay. So, here we introduce internal phase shift to both the bridges and it is same. So, this is the inductor current, this is DPS, another waveform TPS. Achha, this is TPS. So, in TPS now the degree of freedom is much more. So, previously in SPS we had two phasors like this. Okay. And now since alpha 1 not equals to 0, alpha 2 not equals to 0. So, this is alpha 2 and then alpha 3 not equals to 0, but alpha 1 not equals to alpha 3. So, in this case, so this will become somewhere here, let us say this VP phasor, this VP dash now, and this is VS phasor. Now, since alpha 1 alpha 3 are different, now in this figure you see here it is less, it is more, that means this will be smaller in length, this will be smaller in length. So, in that case it is previously when it was DPS EPS yes, when it is DPS it was equal, but here it is not equal. So, VP dash, this is VS dash, okay, and this is alpha 2. So, these things you run the simulation and check whether you can achieve these things or not and how it is affecting the power flow. Also, you have to comment on, so that will be an assignment that you have to submit. You have to comment using which modulation scheme this can be achieved, in which modulation scheme this can be achieved. That assignment, a write up that you have to submit with your comments, that how, which modulation scheme it can be achieved and why do you feel that okay, this is the particular modulation scheme by which we can do this. Okay. So, these two things you have to write and submit same as like previously that you have submitted. Okay. So, now I explain the things. So, now you can share the two files, you share to WhatsApp group as well as in MS Team. So, everybody run those simulation. So, this will be assignment 2. Acha, one more assignment I will give you, that will be based on the first lecture that I gave, that I will write and give it to the MS Team, and that also it will be a small write up that you have to submit. Okay. Okay, then we are stopping here. Reference waveforms are here available, reference waveforms are available here. This PPT we can share in the MS Team for their reference, this PPT, so that these waveforms they can see and they can accordingly they can execute the simulation file. So, first of all, there are 4 simulations. It might take time to execute each and every one and to see the performance. First of all, if you face that you are not able to run the simulation file, then you let us know, and if you are able to run it and if you have any query, so that so here this one is alpha 1, alpha 1, alpha 2 and alpha 3. Okay, I forget to mention it. So, by adjusting this, so for SPS you make alpha 1, alpha 3 0, and then you put some alpha 2 and execute and see whether this result is coming or not. You put alpha 1 not equals to 0 here, alpha 1 not equals to 0, alpha 3 equals to 0, and see whether it is running or not. So, this session I again resumed in order to know that whether you have any query, any doubt, anything that you have. Okay, we forget to share this, I think this PPT we forget to share, right, this PPT. So, this PPT we will share, this PPT will share, so that you can take for reference. Please share this PPT. Okay. So, I am here, if you have any query regarding that simulation running and any other issue, please let me know. Reference waveforms are mentioned in this PPT, that you can see, that PPT will be shared soon in MS Team. Also, I posted one assignment. That assignment by today night you write on a paper your justification, then you scan, upload. It could be soft copy, it could be handwritten also, no problem. Okay. So, just you think on your side, think, justify, and then you write your answer and upload. Because this MPPT tracking and connecting to the grid is a typical problem. This is a problem in the sense of there is a typical application, where what we do is we extract power at MPP and then feed to the grid. Very rarely means there are chances when we work in islanded mode. So, let us say you have a solar inverter. So, let us say you have a DC-DC converter, boost converter, after that you have a solar inverter. So, that solar inverter is feeding power to the grid, and when it is connected to the grid, it is in current control mode. When it is islanded mode, then you have to give some voltage reference and frequency reference in order to work it in standalone mode. So, understanding this is essential actually. How with different, there are papers which explain this phasor diagram, first harmonic phasor diagram, that is explained in many paper. Many paper means at least I went through 4 papers which explain the how you can deal these things with the phasor, because phasor is the best thing to understand when it is AC. So, here it is high frequency AC. So, the best part is by doing this different modulation scheme, by employing different modulation scheme, and then you try to understand from this phasor diagram point of view. Here this side voltage is fixed and you have to keep this side voltage fixed. Okay. So, PPT is available, you can see for your reference. The reference waveforms are given. So, you run the simulation and you can compare with the result that you obtain from the simulation. Now, you can see that there you can play with the angles. It is in open loop mode. In closed loop, you have to control this EPS modulation, if is let us say, then the duty ratio, inner and outer phase shifts you have to control in order to control both the back power flow as well as the power flow from one side to other side. Okay, so, participants will run these files and they will try to see the performance of different modulation scheme. So, we will stop here, we will stop this tutorial 3 session. Thank you. If you have any query, you can post your query in the WhatsApp or in the MS Team that is created. So, we can address those issues whatever is there with this simulation. Okay. Thank you.